Alright, so finally we get to talk about Markov chains. So it turns out we actually know a little bit about the idea of Markov chains. So intermittently throughout the course, we've briefly discussed this idea of a heat equation. And so if you'll recall, a heat equation had these varying heat states along it, and as time went on, those heat states kind of diffused over the entirety of the area that was being heated, and eventually reached some sort of cooled, steady point. And so it turns out that we can go ahead, and in order to make it easier for us to calculate what the current heat state is, we have a matrix that can be easily diagonalized in order for us to go ahead and figure out what happens after a long amount of time to these different heat states. And so this is this process of starting in some place, the transition being described by a matrix, and then you wanting to do that process multiple times, describes a number of different applications. Talks about the movement between of people between regions. So say people leaving and entering different states, different countries, the different states of weather we have. If you notice, there are some times where you'll go on the local news and they'll tell you it's a 20% chance of rain 10 days out, and you get closer and it either jumps up to a much higher percent chance of rain or drops down to a much lower percent chance of rain. So this is all related to the idea of these transition matrices based on what is currently happening. There's also the movement between positions on board games. So say you're on a particular space, the transition matrix then would describe how likely it is you'll land on different spaces depending on what your movement options are. You can talk about your score in games like blackjack, movement between web pages, the positions of runners on a base, and the number of outs in baseball, different things in an ecosystem, and all sorts of other applications. So, for example, say we've got a class that's divided into three groups, A, B, and C. And we get them all into these groups. We want to know, we want to be able to describe when a third of group A goes to group B and a third of group A goes to group C, a quarter of group B goes to group A and a quarter of B goes to C, and half of C goes to group B. We want to know what happens after a few of these transitions. So say we start off with kind of groups A, B, and C. So we're saying that a third of A is going to B and a third of A is going to C, which means, of course, a third is just going to stay in place. We've got a quarter of B. What is already there is going to A, and a quarter of B is going to go to C, which of course means that half of B stays in place. And we have that half of C is going to transfer over to B, but then the other half of C is going to stay in place. So with A keeping only a third of its people each time, sure, it's getting a quarter of the people that are from B, but is there going to be a point eventually where we don't have any people left in A? Or is there eventually going to be some sort of thing if we do this over and over again? So say we start this once, if we keep doing this over and over and over again, will we eventually get to some point where there's the same number of people always, no matter what happens? So this is going to have some things about what's going on, or this is some examples of things that could go on and be an example of Markov chains. So let's get a little bit of an introduction to a Markov chain. A Markov chain, or a Markov process, is a process in which the probability of the system being in a particular state at a given time period depends only on its state at the previous time period. So there's no past in a Markov chain. It's just whatever your current state is, and then what the next state is, based on what you have as your transition matrix. So there are some common questions about Markov processes. First is, do we have any sort of long-term behavior for this process? And is there any stability in the process? What we'd like to know is if there's some sort of equilibrium state we can hit. Eventually we'd like to know that there is some sort of place we get to where we keep going through the process, but everything stays stagnant. There's no changes, and this kind of describes what happens in the long run. So let's suppose on any given class day, you wake up and decide whether or not you're going to come to class. If you went to class the time before, you're 70% likely to go today. And if you skipped the last class, you're 80% likely to go today. So this is maybe not the best example. I'd like to think that if you went to class before, you're consistent and you're 100% likely to go the next day. And I like to think that if you skipped class, the last class, you're even more likely. I don't know how you're more likely than 100% to go, but this relationship of you're more likely to go if you missed, I think hopefully makes sense. Hopefully we'd like to make sure we made up for lost time. So some questions you might ask could include, if I go to class on Tuesday, how likely am I to go to class on Thursday or the next Thursday? Assuming that we have an infinitely long class that goes on forever, which, kind of terrifying for all involved, what portion of the class are you going to end up attending approximately in the long run? So what we're going to do first is we're going to set up what's known as a transition matrix or a stochastic matrix. So suppose we have n possible states in our system. The transition or stochastic matrix for this system is given by a matrix T whose entries Tij are the probability of switching from state J to state I. So the entries indicate probability of leaving the column value for the row value. So in our earlier example of skipping class, we want to know if we are 70% likely to go the next class if we went the time before, and 80% likely to go if we skipped the previous class. We want to be able to figure out what this transition matrix will be. And so we come up with our matrix as such. We have two states, either we're going or we're not going. And that means we have two rows and two columns. One will indicate going and one will indicate skipping. So how we fill these out is we fill out the column to talk about what had happened the time before to what will happen this time. So what that means is that our column entries should add up to 1 or 100%. So the column tells us what happened last time, and the rows tell us what happens this time. So if we went to class, we're 70% likely to go today. So that means we should be 70% likely, if we went to class, to go this time. If we're 70% likely to go to class, then that means there's a 30% chance we're going to skip class. So notice that these two entries have to add up to 1. Now we also said if we skip the last class, we're 80% likely to go today. So that means there's an 80% chance we go, and if there's an 80% chance we go, that means there's a 20% chance we skip. So how we interpret these entries is that if I pick this particular entry, that means that I skipped last class, and there's a 20% chance I'm going to skip again. If I went last class, there's a 30% chance I skip this time. If I skipped last class, there's an 80% chance I go. And if I went to last class, there's a 70% chance I go to this class. So this is going to be our transition matrices, this 0.7, 0.8, 0.3, 0.2. And it does matter which order you put your columns and your rows. So we could go ahead and rearrange this so that skip was first row and first column, and go was second row and second column. And that will impact how we go ahead and order our information. But we'll see a little bit more of that later. All right, now earlier we talked about this idea of going from these different groups. So if we split the class into groups A, B, and C, what happens between all those? So let me have this kind of hover over a little bit. So if we wanted to create our transition matrix here, again, we want to go ahead and create our columns being where we were. So A, B, and C, where we were. And our rows A, B, and C will be where we end up. So we want to go ahead and fill this out based on this information. So if 1/3 of A goes to B, then if we're at A, there's a 1/3 chance we go to B. And 1/3 of A goes to C. So if we were at A, there's a 1/3 chance we end up at C. Again, because that means that we've used a third at B and a third at C, there's only a third left for A. So that means in order to get this to add up to 1, we need to make A be a third. Now if we talk about B, a quarter of B goes to A. So if we were at B, there's a 1 in 4 chance we end up at A. And a quarter of B goes to C. So if we're at B, there's a 1 in 4 chance we go to C. That means that half of B stays put. All right, last but not least, if we are in C, half of C goes to group B. So if we're at C, half of us goes to B. We don't mention A at all, so there's no chance we go from we were at C and we go to A. And if half of us is going to B, the other half of us in group C are staying put right at C. So this would be our transition matrix for this system. So these transition and stochastic matrices have a couple of nice properties that we can rely on to kind of, one, double check what we're doing, but two, they have some nice things go for us. The first property is that all entries are between 0 and 1. So they're probabilities. But more importantly, there's nothing negative here. So also they're non-negative. Or in other words, greater than or equal to 0. Also, all of the columns have to add up to 1. So that would mean then that if we have, all these entries between 0 and 1 and all the columns adding up to 1, that it really helps kind of signify that these are probabilities that we're looking at. All right, so we're going to skip down to definition 13.3. A transition matrix for a corresponding Markov chain is called regular if for some k greater than or equal to 1, that transition matrix T to the k has all strictly positive entries. So strictly positive here means greater than 0. Note this means that there's a positive probability of eventually moving from every state to every state. So that means we're always going to be moving to each possible place. So, for example, this matrix T1001, which is the identity matrix, it is a transition matrix. because it does have that all these entries are between 0 and 1, and the columns add up to 1. However, it's not regular. Notice that if we took 1, 0, 0, 1, we raised it to the k power, that's just going to continue to be 1, 0, 0, 1. So these top right and bottom left entries will never be something that is strictly positive. Here's another example of a transition matrix that we can see after a few states is actually regular. Yes, A is regular. Since a to the third has strictly positive entries. All right, so something else that we want to talk about when we have these Markov chains is a state vector. So we've got this nice matrix that tells us how we're moving about, but we need to know where we currently are in order for us to go ahead and talk about what's going on with the Markov chain. You know, if we're not actually moving something, it doesn't make much difference that we have a matrix that can describe it. So the state vector for a Markov chain with n possible states at a given time step k is denoted by x to the power k. It looks like power, but it's not so much a power. It's really an index. It's a really weird thing that they put the index up here as opposed to, it's a subindex, but that's, its own thing. And this is equal to a vector that has the probabilities of being at each of the different states at time step k. So, for example, this is the probability of being at state 1 at time step k, whereas this is the probability of being at state n at time step k. These vectors are also going to end up being called probability vectors because they're going to have their entries add up to 1, and they're going to be non-negative. So in order for us to find our state vectors for our examples, we would need some information. For this skipping class example, we need to decide what our initial state vector is going to be, so what our x0 is. So here, we would want to, based on the ordering of our columns, decide what we were starting at. So assume for a second you go to class the first day. The order of the entries in our state vector needs to correspond to the order of our columns. So what that means then is, let's say we wanted to go to class the first day. So if we went to class the first day, our initial state would be 1, 0. So this would be going versus skipping. So what this means then is if we took this matrix times 1, 0, our entries should become the probability of going and the probability of skipping based on what that initial state is. So we'll explore this option a little bit, or this scenario a little bit more in a second. But I want to talk about how we can create a probability vector if we're given, say, some numbers that aren't so much probabilities. So we want to find the initial state for the Markov activity we had talked about if we started with 20 students in A, 10 in B, and 10 in C. What this tells us then is that we have 40 students total. So we have 20 plus 10 plus 10, so 40 total students. If we wanted to figure out what proportion are currently in each state, our x0 will come from taking the 20 students we have in A over the 40 total, the 10 students we have in B over the 40 total, and the 10 students we have in C over the 40 total. So this will give us 1/2, 1/4, and 1/4 as our initial steady state. Or sorry, as our initial state vector. Steady state comes in a little bit. All right, so this leads us to theorem 13.1. If T is the transition matrix for a Markov chain, then the state vector for the k plus 1 time step denoted x k plus 1, it can be determined from xk by taking and setting xk plus 1 equal to t times xk. So in order to find the next state, all we need is the previous state, and to take that and multiply it by our transition matrix. So suppose we go to class on Tuesday. We want to know the probability we go to the next class, or the class 3 classes from now. So if we go to class, just a second, I have to fight the cat. Let's make sure the cat does not disturb our mathematics. Hi, Periwinkle. All right, so if we know that we go to class on Tuesday, this is going to describe our initial state. So x naught, if we're going to class, will be 1, 0. If we want to find the probability that we go to the next class, that will be x1. So this will be something we need out of x1. So it won't be the entirety of x1, it'll just be part of x1. In order to find x1, I get to fight Periwinkle today. Whoop. Okay, so in order to find x1, we just need to take t times x0. And so how we do that is we just take the matrix that we found of 0.7, 0.8, 0.3, 0.2, and we multiply it by 1, 0. And this will give us what x1 is. So what we have then is the first entry of this matrix will be 0.7 times 1 plus 0.8 times 0, so 0.7. And our next entry will be 0.3 times 1 plus 0.2 times 0, and so we'll get 0.3. So to answer this question, there is a 70% chance we attend the next class. If we want to know about the class 3 days from now, that'll be x3. So this was one class. The second class, or 2 classes from now, we'll figure out by taking and having our transition matrix times x1, which is just our transition matrix times our transition matrix times x0, or t squared times x0. So you'll see where it would be handy to be able to, raise t to some power. and do it over and over again. But we're not interested in the second one, so we don't need to go ahead and take a second to compute it. We're interested in 3 classes from now. So not the first class, or not the next class, not the class after that. We want to know 3 classes from now what we're going to be in. So this will be t times x2, which we said was t times t squared times x naught. So this is t cubed times x naught. So we'll then take 0.7, 0.8, 0.3, 0.2. We'll take this matrix, we'll raise it to the 3rd power, and we'll multiply it by that initial state of 1, 0. And what we should get roughly is 0.727 and 0.273. So then, that tells us, because we want to know the probability that we go to the class 3 days from now, there is a 72.7% chance we attend the class 3 days from now. Now, recognize that if we knew whether or not we went 2 classes from now, that would change our probability, right? Then our initial state would be 1, 0, and we'd multiply by our t matrix, and it'd either be 70% chance if we went or 80% chance if we didn't. So what this 72.7% chance tells us is that given what we know now, and the fact that we don't know information about the future, or what's going to happen further out, this is how likely it is that we end up attending class 3 days from now, given the information we have. And this is why Markov chains, as we kind of go forward, can change a little bit of what their prediction is. Because if we're trying to predict for something very far out, from a long time from now, it will have a different sense of how likely something is than if we know information sooner. And because we can use these to predict the weather, this is what causes weather forecasts to kind of update and be so frustrating for us. So remember that if we want to go ahead and calculate t to the k for a large value of k, we might want to compute each x sub k from the previous state rather than calculate t to the k power. What would be nice, though, is if we could go ahead and diagonalize this matrix T. So we had talked about how if we could take something to a large power and make it diagonal, then we'd be able to go ahead and easily calculate whatever that diagonal entry was. Now this brings us to the idea behind steady state vectors. So something we had mentioned is that it might be useful to know the long-term behavior of whatever system it is we're working with. So what we really want is to determine the limit as k goes to infinity of t to the k power times the initial state x naught. So let's talk about a couple of theorems and a definition. If T is a n by n regular stochastic matrix, so regular of course means that we should be able to get all the entries being non-zero or strictly positive for a high enough power k of this matrix T. And stochastic meaning we've got all our probabilities, so the columns add up to ones and their values are between 0 and 1 inclusive. Then T has a unique vector u. That is, if x naught is the initial state, then the limit as k goes to infinity of t to the kth power times that initial state is going to be u. That is, eventually our Markov chain states will converge to u. So we start off with x naught, we get x1, we get x2, We keep going for a while, and eventually what happens is, no matter how many times we multiply by our matrix, we get back this vector u. The u that we've just described is called a steady state vector. What that means is that for a large enough value of I, the state xi is going to converge to u. And then the next state will be equal to u as well, and the state after that one will be equal, and eventually we'll just have our system stay the same. And then xi plus 1 is going to equal u, which equals t of xi, which also equals u. And we have this process go over and over and over again. And this is going to describe our long-term system of the system, or behavior of the system. All right, so we have this nice theorem. The steady state vector for u is the unique probability vector satisfying the matrix equation t times u equals u. Well, wait a minute. So if t times u equals u, what that tells us then is that t times u equals the identity times u. Okay, why do we care about that? Well, what that tells us is that t times u minus the identity times u equals 0. Well, why do we care about that? So that tells us that t minus the identity times this vector u, which we know is not 0, equals 0. Well, hey, wait a minute. That sounds a lot like this eigenvector stuff we've been working with. Well, what that means in the end is that u is an eigenvector for the associated eigenvalue, and it's not just any particular eigenvalue. If we're looking at just subtracting off the identity matrix, that eigenvalue is 1. Well, that's exciting. That's really cool. So all we have to do is know how to do eigenvalues and eigenvectors, and we don't even have to find the eigenvalue. We know the eigenvalue. It's going to be 1. So we just need to go ahead and find the eigenvector. So how do we find a steady state vector? Well, first we want to go ahead and find the eigenspace associated with lambda equals 1, then create a probability vector by taking whatever that vector is and dividing by the sum of the entries of that vector. So, for example, if we find that the eigenspace associated with 1 is the span of 1, 4, then our steady state is going to be, SS, is going to be 1, 4 times 1 over 1 plus 4, which will just be the vector 1/5, 4/5. So that means that those entries will add up to 1, and they'll be between 0 and 1, and everything will work out nice for that. So that's how we find steady state vectors. So let's go ahead and find one for this skipping class example that we talked about. So we want the null space of t minus the identity, because that's how we find our eigenspace associated with that particular eigenvalue. So we'll take then the null space for 0.7, 0.8, 0.3, 0.2, not ready yet, minus the identity, which is just the null space of negative 0.3, 0.8, 0.3, negative 0.8. And what we'll end up getting when we go ahead and bring it over to the side is negative 0.3, 0.8, 0, 0.3, 0.8, 0. Get the reduced row echelon form, and we should get 1, negative 8/3, 0, 0, 0, 0. And so when we want to go ahead and bring this back into creating a set with a condition, it means we have the set of all x, y such that x equals 8/3 y, which will mean we have the set of all 8/3 y, 8/3 times y, y, such that y is an element of the real numbers, which is just going to be the span of 8/3 1. But that doesn't give us our probability vector. In order to get our probability vector, we need to go ahead and be able to turn this into something where the entries add up to 1. So we need to divide by the sum of this entry. So two ways to do this. One way is to take 8/3 1 and multiply it by 1 over 1 plus 8/3. But because we're dealing with the span, what we have is all potential multiples of this vector. And so we could multiply by the least common denominator, in this case 3, and use that as well in order to find what our probability vector is. So we can use 8, 3 times 1 over 8 plus 3, and in either case, the vector we'll end up getting, you can try both and see for yourself, is 8/11ths, 3/11ths. And so this is going to be our steady state vector. And so what that tells us is that there's an 8/11 chance that we end up going to class long term on any particular day, which is found by this probability of 0.727 with the 27 is repeating, and 3/11 is our probability of skipping class on a particular day. So let's get those numbers down, right? We don't want to have a 27+% chance of skipping class. That would not be ideal for learning. All right, so there are a number of applications for Markov chains, one of which we're going to see right now. So we're going to go ahead and talk about Google's PageRank system. So Markov chains gets used for Google to go ahead and help rank the pages and determine the quality of a page when you go ahead and search some term. So this is going to be a very obviously we don't have all of the proprietary information for the Google PageRank system, but we know enough things that we can come up with a small example. So we're going to start off with some assumptions. The first assumption is that Google treats everyone as a random surfer of the internet and assumes you're going to randomly choose links to follow. So you're going to end up on a page, you're going to think, oh, hey, well, there's a link on this page, maybe I'll click it. And if there are links on the page you're currently on, there's an 85% chance you follow one of the hyperlinks on the page, and there's a 15% chance you just randomly you randomly go ahead and go to any page on the internet. You just type a page you're interested in, and you go there. Now this includes the page you're currently on, and the way to think about this is there's a chance you always refresh the page you're on. So there's a chance you end up back on the same page you're on as well. If there's no links on the page you're on, which we'll call a dangling node, then you're equally likely to jump anywhere on the internet. You could go right back to your current page as well, and this is what helps make us have a regular transition matrix. So there is an example on your homework as well. Actually, I don't think it's on your guys' homework. Let me cross that out. It is a cool problem. But here, we want to look at which page or pages are dangling nodes. So a dangling node is one where we are equally likely to jump anywhere because there's no links leaving that. So there's a link leaving 2, a link leaving 1, links leaving 4, a link leaving 3, links leaving 5. So 6. This is the dangling node. Alright, so this is going to be probably one of the more complicated examples we will see, but this will help us go ahead and be able to set up transition matrices based on our probabilities, and then we can go ahead and find our steady state. And our steady state is what we use to go ahead and rank the pages. So here we have a directed graph that represents 4 web pages representing links to other pages. We want to create the transition matrix for this Markov process. So what we're doing is we're going to figure out our probability of going from one of these nodes to the others. So remember, for each of these, we need to go ahead and find the probability of using the web page, or using a hyperlink on the web page, and the probability of randomly clicking on any page. So 85% chance link followed, and we're going to treat all those links equally, and there's a 15% chance of randomly going anywhere. All right, so in order to set up our transition matrix, we need to figure out for each of our columns which page we're starting at. So let's start off with page 1. So if we go from page 1 to each of these different pages, we'll use these to fill out the first column. Okay, so page 1 only has a link going to page 2. So because there is a link going to page 2, 85% of the time we're going to jump from page to page 2. And that's the only matrix, or the only web page we're going to go to with a link from page 1. So how we'll do this is we'll take, for page 2, we'll take 0.85 times 1 over 1. We'll talk about why I'm doing 1 over 1 when we have something more interesting with more links. Plus our 15% chance of getting there randomly from any of the 4 pages. So 0.15 times 1 over 4. So let's make sure we can set up each of these equations going from page 1 to whatever page as we go. So there's no link going from page 1 to page 3 or page 4, so we don't even bother with the 85% chance. The only way we're getting to page 3 or 4 from page 1 is by taking into account the 15% chance that we randomly get there, divided evenly amongst the 4 pages. So that's why we're multiplying each of these by 1/4. And again, page 4, we don't have a link from page 1 to 4, so we only have the 0.15 times 1/4. Now again, there's no link going on 1 to itself, so this will follow the same probability. So as we create our T matrix, this first column will talk about being in page 1 and going to pages 1, 2, 3, and 4. So if we want to go ahead and calculate this 0.15 times 1/4. We'll get 0.375, or they give us some fractions, 3/80. And so that'll be true for page 1 to page 1, page 1 to page 3, and page 1 to page 4. Now, in order to find our probability of going from page 1 to page 2, we'll take our 0.85 times 1 plus our 0.15 times 1/4. And let's make that a fraction. So we'll get 71/80. So again, what you'll notice is that all of these entries add up to 1. So if you took all 4 of those and added them together, you'll get 1. And they're all between 0 and 1. All right, now let's go ahead and look at page 2. So page 2 has no links leaving it. So this is a dangling node. So what that means is that going from page 2 to page 1 to 3 or 4, these will all be calculated the exact same way by taking the entire 100% and dividing it amongst the 4 pages. So we'll end up with a 25% chance for to end up on any page if we're currently on page 2. So this will be 0.25. Don't know why I wrote it as 0.25. I want to write more fractions. 1/4, 1/4, and 1/4. That'll be the only blemish on an otherwise perfect matrix. That sentence basically set me up to make a mistake. So warning that it's probably coming at that point. All right, now when we're on page 3, we want to figure out the probability of going to any of the other pages. So again, we want page 3 to page 1, page 3 to page 2, page 3 to page 3, and page 3 to page 4. So for any of these pages where we are currently on 3 and we're going to follow a link, notice that this between 4 and 3 is a double, it links both ways. So 3 goes to 4 and 4 goes to 3. So 3 actually has 3 links leaving it. So they all are going to split that 85% of following a link evenly amongst them. So we should have 0.85 times a third. But there's also a chance we randomly get there on our own. So we have the 0.15 times a fourth. And this formula will be what we follow for every page that page 3 has a hyperlink going to. Now, the only way we get to page 3, because it doesn't link to itself, you know, like some articles on the internet I've seen, rattle saber at them, is by using that random chance of, you know, refreshing the page. So we have our 0.15 times a quarter. So again, in order to calculate all these, we'll use our handy dandy calculator. So for page 1 or 3 to 1, 3 to 2, and 3 to 4, we have 0.85 times a third plus 0.15 times a fourth. And so again, I like fractions, and this gives us for each of those 77 over 240. So that's 1, 2, and 4. And then for our page 3 to itself entry, we have 0.15 times a quarter, which gives us 3 over 80. So the last thing then to figure out, boy, aren't you glad you stuck around for this example, is how we calculate the probabilities from page 4 going to anywhere else. So page 4 to page 1, page 4 to page 2, page 4 to page 3, and page 4 to page 4. So if we wanted to go ahead and find these probabilities, page 4 has a link going to 1 and to 3, but no links going to 2. So when we're looking at pages 1 and 3, we'll be taking our 0.85, dividing it between those two pages, so times a half, plus 0.15 times a fourth. Because again, we always have a 1 in 4 shot of going to any of these other pages. And then for both pages 2 and 4, we only have our chance of randomly getting there by randomly going to that page, or in page 4, it's probably refreshing. And so we will go ahead and calculate those probabilities. Now what's nice is this 0.15 times a quarter is something that shows up in a lot of these other columns. And so we end up with 3 over 80 and 3 over 80 for both of those entries. But for these other entries, these 4 to 1 and 4 to 3, we have to calculate 0.85 times a half plus 0.15 times a fourth. And that'll give us 37 over 80. So again, you can check, if you add all these up, you'll end up getting 1, which is what we should expect. And so we found our transition matrix T for this system. Okay, so now that we have our transition matrix T, we need to go ahead and, since it's a regular matrix, we could find a steady state vector. So in order to find this vector, we want to go ahead and find the null space for T minus the identity. So let's go ahead and do that with our calculators. So first and foremost, we should go ahead and store this T matrix. I'm going to store it in A. So it's a 4x4 matrix, and its entries are going to be 3 over 80, 1 over 4, 77 over 240, 37 over 80, 71 over 80, 1 over 4, 77 over 240, and 3 over 80, 3 over 80, 1 over 4, 3 over 80, and 37 over 80, and 3 over 80, 1 out of 4, 77 over 240, I don't know what happened there, 77 over 240, and 3 over 80. Okay, so we've got all these entries. We also need to create an identity matrix, 4 by 4, 1s along the diagonal, 0s everywhere else. So we want to go ahead and take A minus B. We should get this matrix. What we're going to do is we're going to store that in a different matrix. See if this works. And so now our matrix C should be that matrix we had. And so what that means is that we can get the reduced row echelon form of this matrix C, which is found from our other things, and we want to go ahead and make a fractional version of that. So we have this lovely series of fractions to deal with. So what we have then, so let's review what this tells us then from our equations. It tells us the first variable is going to be 57 over 40 times the last variable. So if we had w, x, y, and z, we'd have w equals 57 over 40z. We'd have x equals positive 1,769 over 800z. We would have y equals 171 over 54z, and we'd have z equals itself. So this is going to be then the set of all w, x, y, z such that W equals 57z over 40. X equals 1769 over 800z. And Y equals 171 over 154 z. So then we have as our null space the set of all 57z over 40, 1769 over 800z, 171 over 154z, and z, such that z is an element of the real numbers. So that's going to be just the span, and I'll write it horizontally now, of 57 over 40, 1769 over 800, 171 over 154, and 1. So we need to find a probability vector using that. So what we'll do is we'll take this 57 over 40, 169 over 800, 171 over 154, 1, and we want to divide by the sum of all of those. So times 1 over 57 over 40 plus 1769 over 800 plus 171 over 154 plus 1. And so what we'll do is we will create a vector D 4 by 1. We'll put in all of our entries: 57 over 40, 1769 over 800, 171 over 154, and 1. Then let's see if there's a way to sum these. Let's try this. Maybe it'll work, maybe it won't. That did not do the thing that I think we wanted it to do. So we're going to take this matrix, D, and multiply it by 1 over the sum of each of these. So 57 over 40 plus 1769 over 800 plus 171 over 154 plus 1. Error data type. Let's see what happens. Okay, it does not want us to do that. Well, that's going to be a problem. So let's see if there are any other matrix things. This is very easy to do on Octave. Octave never gave us all these troubles. Alright, so we're going to do hard mode here. We're going to try to show you Octave. Right now we're showing you the screen that it is on, which is not as helpful. Yay, troubleshooting at its finest. Alright, so I'm going to go ahead and go on Octave and do this. This might be promising. Hit that button. Okay, so now we're getting left, right. No, we're upside down still. Do this. Right side up. We are right side up. Okay, great. So let's go travel to the world of Octave. And together we will see what we have. Okay, so right now you're not seeing the part of the screen I'd like you to see. Now you're kind of seeing the part of the screen I'd like you to see. Okay, so we have this vector, which we've said now is 57 over 40. 1769 over 800, 171 over 154, and 1. So there's our vector. And we'd like to go ahead and be able to divide it by the sum of the entries. So the sum of the entries is going to be found by taking sum of v. And so we can create this new vector w, which will be v divided by the sum of v. And that'll give us this vector. Now what's nice about this is Google's PageRank wants us to go ahead and rank it based on which has the highest probability. And in this form, that's really easy to see. We would obviously put page 2 first. We then follow it up by putting page 1 next, and then page 3, and then page 4. But sometimes we want to go ahead and see these in fraction forms because it's way easier to check that if your name is Mr. Smith, and kind of verify that it's what we think it is. So this is the fractions we should end up getting. These do not look like the fractions I saw before, which makes me think that somewhere along the line I typed something in wrong, whether it be in the transition matrix T or something along the lines. If you find something wrong with this, or something that we did here, feel free to mention it on the discussion board. But for now, we're going to go ahead and assume that everything there was hunky-dory, and we have our proper steady-state vector. So note at this point we're just kind of assuming it's a calculator error thing, but the process is all there for what we want. So our steady-state vector should be 1711 over 6,900, 339 over 881, 519 over 2,686, and 1,488 over 8,551. So this should be, little thing separating those, our steady-state vector. All right, so if you've stuck around with me this long, hour-long video, I'm impressed, first of all. Congratulations, you made it to this video. And then the other thing I want to mention was that after this is an ice sheet where you get to kind of practice some stuff involving Markov chains. So a couple of pages, 5 problems. Go ahead and give it a try, and then tune into the next video.